Welcome to episode 18 of Roid Rage.
We're legal.
That's, 10 seconds in, we're already editing it. I like it. Today, we're going to try not to get canceled, and we're going to dig into the part of the spacecraft that basically controls everything, our power. So we're going to talk about avionics with our head of avionics, Chris. He's been leading the charge on all of our building new avionics for Vestry, and I think we want to learn a couple things today. Who you are, why you care about avionics and deep space avionics, and how it's different than how a lot of the companies think about that. So before we get into the details, Chris, who are you and how'd you get interested in this?
That's a good question, actually. I'm Chris. That's who I am. I'm, as we were just discussing before the podcast, I'm from Arkansas.
Yeah, the great state.
The great state of Arkansas. I've been on a lot of places since then.
Okay.
By way of, I spent a lot of time in Florida and some time in Arizona, a lot of time in Washington State.
God, anywhere cool?
Washington State's really
Yeah,
nice.
actually, Washington's pretty nice.
Really nice, yeah.
Okay.
Currently Tahoe and here, splitting my time. But mostly here because, as you said, I've got to make the avionics and the power system for this. No pressure, though, right? Everything has to work.
Yeah, it's a minor component.
Right. So, funny story how I got into engineering, I guess. When I was in high school, I had a very bad idea that I wanted to be a lawyer. I have no idea why. I guess that stuff interested me at the time.
Okay.
And then I was looking for a degree that A, would allow me to get an undergraduate degree and go to law school, and B, would be able to get a job if I didn't go to law school.
Okay.
I had absolutely no idea what an engineer did.
Wait, that's why you picked it? That's like the dumbest logic I've ever heard.
It is. It was
because
terrible.
how many lawyers are engineers?
Well, the patent lawyers are all engineers.
Oh, so you're a patent, like the worst kind of lawyer.
I
patent lawyer?
didn't. As I said, I didn't know what what a lawyer did. I didn't know what an engineer did at all. Although when I was a kid, my favorite show was Star Trek, and Scotty was always super cool. But I didn't.
Can we be honest about? I guess this is going to be Star Trek. Is like it's terrible.
It's great.
It's just.
If you're going to say it's terrible, you've got to present either a case as to why it's terrible or an alternative to what is better. You can't just come out here and just have a hot take and have that go.
It just has no personality. It just is not what a spacecraft would ever look like. It's not based in physics. And what is a Klingon? It's like the dumbest thing ever. Like you just picked a reptile and put some dude in a mask and here's a native language for it. Like it's just terrible.
That's what they did with all of the aliens. They just make them look weird,
So you just love sci-fi as a category is what you're
I actually do love sci-fi. I hate Star Trek. Like it has no entertainment value. Like entertain me. Nope. They were like, no, we don't want to do that. We want to be boring.
All right. Well, I realize the trap in asking this. What is your favorite sci-fi then?
I'm sure it's going to be terrible.
Probably my favorite sci-fi series is like the Alien series.
Oh, that's not terrible.
That one's pretty good. Star Wars can be fun until George Lucas sold it to Disney, and now it's just pure trash.
Have you seen Andor?
Andor's fine. Like it's great, but it's also like comparing like a moldy sandwich to a sandwich that just doesn't have mold on it. Like I'm not going to say it's great. It's just not the shit that George Lucas sold to Disney and whatever
great,
Disney did.
And the new movie, the Rogue One, rolling into Rogue One.
Rogue One was fine.
Great.
7, 8, and 9 are probably the biggest abominations I've ever seen in movie history. Like who greenlit that? Who was like, hey, let's have no cohesive story and like we'll just Palpatine comes back and he's like a dude and there's what is going on? Like sucks.
I realized that there's a big debate. And I didn't know this before, is about whether the prequels were worse or the sequels were worse.
There's no debate. The sequels are worse. The prequels are bad.
I actually thought that the sequels were better than the prequels, but I find that there's
That's why you like
big
Star Trek.
split there. Anyway.
Yeah. So patents.
I'm not going to talk about Matt's taste in stuff.
Sorry, it's questionable.
It is questionable. A lot of taste that Matt has is questionable, but that's all right. Anyway, back to Scotty. So he was an engineer. I didn't know what an engineer did. Of course, if you watch Star Trek, you still don't know what an engineer actually does because he just gives bad schedule estimates. I mean, which is a key, skill for an engineer is to be able to estimate how long it's going to take to do something. But he always overestimated, and he looked good, right? I have the opposite problem sometimes. Anyway, so then I of course went to school and it was good in physics and math, and I was good in physics and math, so I was like, that was the other reason, is like I thought I could actually pull it off, and I did somehow manage to pull it off. And then I started out at some internet startup business back in 2000 because somebody wanted me to come.
Was
that pre or post bubble?
It was right as the bubble was popping.
Nice.
So I worked for a year in this internet startup, and then I was at a bar in Florida looking for a new job in the time.
To be clear, were you looking for a job at the bar?
No.
Or you were just at the bar?
I was at the bar while I happened to be looking for a job, and I saw this girl sitting at the bar. Oh my God, she's talking to somebody I know. I'm going to go talk to them. So I went and talked to him, and we got to discussing things, and it turns out that her uncle worked at Honeywell in Clearwater, and she was like, he's on vacation. She can come. You should talk to him when he comes back. And he pointed me to a job fair they were having there with like 400 other people or something like that. And I walked in, and they had like a defense and a space side. And I happened to hand my resume to the guy from the space side.
Okay.
And he looked at my resume and he's like, we're not hiring any IT jobs. And I said, well, I'm not looking for an IT job. And then he looked back down at my resume and sees where I went to school and all this stuff. And he was like, okay, well, we'll give you an interview. And I got an interview. And
Wait, what did you get your degree in? You just said engineering.
Electrical engineering.
It was an electrical.
Yeah,
Okay.
Electrical engineering. So then I started doing space. And that's literally by complete luck, blind luck.
Some random girl at a Florida bar.
Yeah.
So you joined Honeywell Space Division. What were you working on?
I was working on geo satellite stuff mostly that I couldn't know what it was.
Okay.
A lot of spy stuff, but not. I never had a clearance, but I worked on stuff that I couldn't know what was doing all the time.
Give us some details. And what did you learn that you weren't supposed to know?
I didn't know anything I wasn't supposed to know, but I was like making this huge space. Well, actually, just a funny story for that too. I walked in, I was working in a special projects thing, making this huge space recorder. We were stacking it with 3D Plus, who we were getting our flash from now. But they were, at the very beginning, they were stacking like 1 gigabit SSD RAM. Like that was the massive size you could get back then. And they were stacking them like 6 or 8 high for us, and in their little gold plated things. And we were taking them and we were putting 72 in a bank, and we were taking that bank and multiplying it by 6 and for a board. And then we were putting like 8 of those boards into a box. And it was the space serious data record, some data recorder thing.
So GeoBirds can hold like 3 terabytes of data?
Yeah, exactly. But it was funny because I walked into his office and he's like in charge of the special projects, and I had no clearance. And I looked at him. And that was at the time there was this story in the news that Congress was freaking out over the cost of this satellite program that they were doing, that they said was going to be obsolete in technology before it got done. And I walked into his office and I said, I know that you can't tell me this, but that's exactly the program we're working on, isn't it? And he's like about to explode, of course, because he can't tell you anything. But yeah, that was it. So it was just a big data recorder. So, but I also worked on I got to work on the space shuttle main engine controller, but what I was working on didn't actually fly because the program got canceled because things happen.
Yeah.
Wait, hold on. So you were working on an upgrade to the RS4 engine controller.
Yeah.
When they knew they were going to retire shuttle.
You know how government spends money sometimes. I'm not sure that they knew that they were going to retire it at that time.
What year was this?
It was, let's see, that would have been in 2001, 2002.
Okay, yeah. Last flight of shuttle was 2012, I think.
Yeah.
So
it was.
Okay.
It was before the second accident.
Hold on. So let me get this straight. You developed a new engine controller. It's 11 years before shuttle was going to retire, and it still didn't make it on the space shuttle?
Yes. Yes, it was actually kind of a cool system because it was a quad. The board I was working on was a quad DSP board. It had 4 DSPs on it, which would probably do about as much as your calculator these days. But it was supposed to sense vibrations in the engine that something was going to go wrong, and then throttle it back a little bit, as opposed to having you had like a binary at the time. It's like you're either on or something's going wrong, and you got to shut it all the way off. And we were trying to develop a system where they could throttle it back some because they've, bad vibrations or something like that. But it never flew because, well, it got canceled. That was a really weird day to go in after shuttle blew up because we were like half of our factory was half of our building was like sectioned off as for investigation and stuff.
Did they
So
bring the parts of the shuttle back to?
They
Florida?
always did every time.
Oh, really? So it
Yeah.
was in your building that you saw the shuttle parts.
Yeah, they would. This is why one of the reasons the shuttle costs so much, because everything's reusable, except that they would have us. They would take the thing apart and ship us back the box, and we would go through it every time, and then refurbish it, and that kind of reuse. Rebuild is basically every time that went. That's why it costs so much. But yeah,
Damn.
so that's how I got into space.
Okay.
Complete luck.
Okay.
But it was exactly what I needed to do because I love doing it. I don't know. I guess I was just lucky instead of being smart and finding what I wanted to do. I was just lucky. Worked
So
out.
after your engine controller never made it to space shuttle and it blew up and all these things went wrong, what happened? Did you stay at Honeywell or did you leave?
No, I was there for a while after that. And then I worked on I worked on Orion. The last thing I worked on there was the Orion program, doing the Orion data network, which is time triggered gigabit Ethernet over, so you could put rocket commands over it and all deterministic and stuff. Very expensive. Spare no expense. So we had, that got me out to Austria once. That was great. That was the last thing I did for Honeywell is they sent me out for a business meeting for like a week in Austria to do a FPGA review. I went to my boss and I said, I think systems ought to have a representation at this meeting. And he's like, yeah, we should. Can you go? And I was like, that worked. And so I got to go to Austria right before I took a new job and quit as soon as I got back. So that was pretty great.
Good to know. No business travel. All right. So where'd you go after that?
I went to Arkansas Power Electronics, and because I wanted to learn about power electronics. Really, I had been doing digital stuff. All was digital, digital avionics, kind of like the flight computers and stuff. Single board computer kind of work. And then I'd moved into systems. I did a lot of systems work at Honeywell as well. But then I wanted to get into power. My wife, who was used to be my job searcher, she told me that I could do better if I had power. She was right about that because it's really in demand. As you can tell, we're still looking for power engineers. So I went there. It was in my hometown too, which was getting a engineering job in Fayetteville, Arkansas is nearly impossible. If you want to work for Walmart, you're in there, or Tyson. You can do all that, but
But so you actually wanted to go back to Arkansas?
I did.
Why?
Well, Fayetteville's a nice place.
It's not. Like, what's the temperature right now? It doesn't matter. It's in the south. It means it's 100 degrees and 100% humidity probably right now.
It's probably pretty warm right now, but it's not. It's in the very north part of Arkansas. It's almost more Midwest than deep
almost
south.
more Midwest. It's still
Yeah.
No. You just know. How big is Arkansas across? Like 400 miles?
I don't know. It's about when I used to drive to Florida, it was about 6 or 8 hours to drive, but it was like I had to drive diagonally across the whole thing. It was.
What's the temperature right now, Chap?
It's 90 degrees with only 60% humidity.
Yeah. See?
I guess it's 3 p.m. So
yeah.
Yeah.
Yeah,
Heat
I
of
still
the
don't
day.
want to. Nope, I'm good. Nope.
Yeah.
Yeah.
And that's a nice day.
I understand. I mean, I just drove across the Mojave Desert, so it would be really nice. In fact, on the way up, when I got the AC went out in the car, of course, right before I drive across the Mojave Desert.
But you notice what you said different about this than Arkansas is you drove across the Mojave Desert to a place that is not the Mojave Desert.
I did, yeah. It was below freezing when I got home once this week. Like a couple days ago, it was below freezing when we woke up. Which was crazy.
Okay, so you moved to the armpit of America, also called the South.
There are
and then
workplaces,
where'd you go after you realized that was not the place to be?
I went to Washington. That's we realized what happened was that it was a silicon carbide company that's now part of Cree. But we were doing some testing and realized that silicon carbide wasn't great for space, and so I still wanted to do space at the time. So I got a job at Aerojet doing for power systems for the propulsion, electric propulsion power systems. And that was cool. I spent a lot of time, like 5.5 years or so doing that.
Did any of that fly?
Oh yeah. Yeah, absolutely. And some of it's already broken up. Yeah. It was,
can you go into more detail? Like, what do you mean it broken up? Like the shit exploded?
there was recently, maybe it's a couple years ago, Intelsat had a satellite and geo breakup. That was
the Russians.
Was it? I don't know what happened, but I know that my propulsion system was on that.
Gotcha.
I don't believe.
Yeah, did we
it.
ever find out why? I mean, there was a whole bunch. It was like micro. I don't think we'll ever know. People
never
say
even
micro
looked.
meteorites or whatever.
I didn't really want to know because I had hardware on there. So
Yeah.
Okay.
Okay. So you do that for a little bit. You get some EP in space. You've now built that. Then what?
yeah. Then somebody asked me if I wanted to come down and work on batteries down here, and I did. I did that for a couple years in the Bay Area for a dinosaur aerospace company that had bought a small startup in San Francisco, or actually in Burlingame, but
Very different.
Same place. What was it called?
they're both the Bay Area. It was Eagle Pictures, the company that I worked for. Lithium Start was the name of the startup. But after a couple of years of varied success integrating the startup with the dinosaur, and by varying, I mean poorly integrating, they decided to close that and asked me if I wanted to move to Rhode Island, which is a nice place.
I was born there.
But the
It's
answer
not.
was no.
You were born in Rhode Island.
was,
That's where
yeah.
the Newport Folk Music Festival is, right?
Jazz Fest. Well, yeah, I guess there's folk and jazz.
Like the only reason I noticed, I just watched that Bob Dylan movie,
Mm.
and it was all about that festival, and it's just like this place looks terrible.
I mean,
I've
if
seen
you
Bob
like fried
Dylan.
clams.
I've seen Bob Dylan multiple times. He sounds like Scooby Doo live.
Bob Dylan is way too old to be performing at this point in time. He's got some amazing songs in the 60s, not in the 2020s.
20 years ago, he still sounded like Scooby Doo live a lot, especially if the sound wasn't great. I can't remember where I saw him. Somewhere the sound was terrible, and it just all sounded.
I mean,
like
he's a
Scooby-Doo.
great writer and a great songwriter, and just
Bob Dylan's
I think
great.
that's it.
He's great. I don't have to qualify. I don't want to
No.
like segregate. He's just great.
Yeah.
But yeah,
Okay.
I understand where you're coming from.
Okay, so you didn't want to go to where Bob Dylan was, and so what happened?
Let's see. I started working for a car charger company that was making car chargers with big batteries in it, called FreeWire. But they'd started out with wanting to do wireless charging, but they ended up doing battery integrated chargers, which
Okay.
is how they got their name. That had
Yeah.
nothing to do with what they were doing at the time. So worked there for a while. Learned a lot about charging cars and big battery systems, dealing with big battery systems, because it was I don't know, 360 kilowatt hour or something like that. It was a huge battery. It was basically a car battery inside the charger. Yeah, and then wanted to get back into space, so I went to Planet and was there for a couple of years. And
What'd you do at
down
Planet?
there, I managed too much. I did too much management. That's what I did. It's a lot of managing. I came in and the system was already designed, and we were trying to implement it. And yeah, it's not a lot of fun to implement a system that you didn't have anything to do with putting together. Great place, but the work wasn't.
Yeah.
There's a lot of management.
Yeah.
I,
Okay.
I much more enjoyed the not management side. So I went to Maxar for like a year, and I did systems. I worked with the systems group.
Where was Maxar located?
Maxar's in Palo Alto.
Okay.
Yeah. So I was on site in Palo Alto for a while, but most of the time I spent in my office at my home in Tahoe, in my pajamas most of the time. So I actually left that job I left a job that I could do in my pajamas to come and do this, because it's fun.
Way fucking cooler.
It is way.
Why'd you move to
cooler.
Tahoe?
Well, if you ever tried to buy a house for a family in the Bay Area, you know that's not happening unless you've already gotten paid out, in some startup. So we got really tired of renting. Our landlord, my last landlord was horrible, and it kind of scarred us.
Yeah.
So we were like, we got to buy a house, and we looked around, and like that was it. That was the only place I could buy a house. That was, well, I mean, I could have bought
Arkansas.
a house in terrible places, but,
Yeah.
or
Okay.
Arkansas.
Yeah.
But I mean, my house in Arkansas, when I bought a house in Arkansas, I think I paid I paid like $220 for a house in the country club. Yeah. Different kind of economies of scale there.
Supply and demand. Real kicker. Real economic viability there.
So you've done a bunch of space.
Yeah.
Why come here?
Because it's cool. We're trying to land on a fucking asteroid, man.
So are you going to be the one who builds the landing legs? Is that there's a
I don't know.
Okay.
Do you need legs to land on an asteroid?
Yes.
Well,
I mean, the definitive solution, absolutely you do. I don't know why this is a
that's
question right
somebody
now.
else's problem, not mine. I just got to get us
right.
there.
So it's cool. What like I'm going to segue this into like, how is it cool from an avionics perspective? And like, maybe before you answer that question, can you define for folks like, what is avionics?
Yeah.
And tailor this to your. I don't
Sure.
care about Webster. Like, what is Chris's definition?
Well, here to me, avionics is everything where we purposely flow electrons through.
Okay.
That's what I call it here. I think
Okay.
that covers the RF comms kind of stuff. It covers the power. It covers the flight computers.
I like how you said purposely.
Purposely, yes. Well, sometimes they don't go where you want them to go, and that's the structure's problem normally. Although it's probably the electronics' fault. But yeah, so I guess in another way to look at it, we have the power, we're generating the power. That's part of it, which, but the avionics, the pure avionics part is probably more like the flight computer and all the sensors, the interfacing with all the sensors,
Okay.
it basically takes all the data from the spacecraft and allows the flight software team, the GNC team to control the spacecraft and sends out commands back out to the, like the reaction wheels and, the propulsion system and all that stuff. It's basically the brains
Yep.
of the whole spacecraft, so you got the power system and you've got the brains and that's that's what the avionics is.
Yeah,
to
the
me.
power system's the heart, and the flight computer's the brains.
Yeah, basically. That basically covers it.
So how disappointed were you when you showed up and realized that there was just an entire system that we had designed for you and you just had to manage it?
Oh yeah, that was how I come. Yeah. No, I was. It's what do they call it? Greenfield or blue sky or whatever.
Yeah,
it's
whatever the
complete. It was a
business school is
completely
saying, yeah.
whatever the corporate speak is these
Yep.
days for that. It's a blank whiteboard when I got here that. We had some space heritage that we'd used, I guess, but most of that was designed by somebody else.
Yep.
It was basically integrating a bunch of pieces from other systems, right, to put together into the last spacecraft. And this one was, it's pretty much a whole system from scratch.
Okay.
So I got here and I didn't feel like I was constrained by what we'd already done.
Well, the power system is, right? So the power system is, we, on the previous spacecraft, because of the time frame, had to buy a lot of parts from Pumpkin and some other suppliers to make sure we could put it together. Core construct is the same, right? It's actually the same number of solar panels, the same number of wings. It is the same technology, underlying technology to do it, but it is much higher power, right? Odin had about 150 watts of total power that it could generate on its list. We can generate now about 2,100 watts of total power. So
Yeah.
it's like over an order of magnitude step up.
Yeah, so I just had to select everything on the screen and grab the bottom little corner and drag it till it's bigger, and I'm done.
The good thing is it's all square area, so it only has to be like 3x bigger,
Right,
in each
exactly.
dimension.
Yeah.
So
Yeah.
Yeah. So where do you start? Clean sheet. Like you walk in day one, Matt's like, great, I need.
So what I did is I came in to see where everything was at, and my initial going in point everywhere is everything is fine, and I just need to continue doing what we're doing.
Okay.
And as I did that, of course, I run into things that aren't fine,
Yep.
and just fix them. Right.
What was the first thing that wasn't fine?
Gosh, what was the first thing that wasn't fine? I mean, all the decisions, like the processors picked out was pretty good, and all there's a lot of stuff that was good, but there was also like, we want it to do everything. And it became, it's a little bit of a packaging problem because you've got to fit, we've got these boards and we've already picked out what the size, we've already picked out the back plane. So I'm kind of working with all that. Because it's not, maybe next time we'll probably build our own stuff a little bit more custom, like a back plane, but it works now. So it's like shoehorning the functions into the size of thing that I have, and I've already expanded by one board, which fortunately we were smart enough to have an extra slot, right? So sometimes we get all of the things together that we want it to do, and a lot of times in the very rigorous old space dinosaur kind of company. We would have spent like a year figuring out exactly how size everything was, defining every requirement, to the, dotting the I's and crossing the T's, and then doing these massive real estate studies and figure out, oh, well, we need to move this stuff around and done all that. But here, I just took everything that needed to go on the board, tried to put it on the board. It didn't fit. Okay. So, well, we'll put it on the other board, so I moved some of the stuff off to the other board, to give myself more room. So it's really, there's a lot of, there wasn't a lot of the design there, but, a lot of the idea, and, Ashton, in the systems has done a good job of defining what the functions need to be. And when getting in here and just working with Ashton really was a lot of the things, in the first month was really making sure that we had everything in the right spot. And things are still moving around, frankly, up to this morning.
Yeah. How did it feel coming in on day one and being late?
It felt like I was working on a space program, actually.
The real hard thing about these space programs, though, is what we're actually getting at is there's this like very complicated build versus buy decision you have at every step of it. And obviously, because of the time frame at Odin, we had a lot of more buy than we did build. And it goes all the way down to like, do you go roll your own ASIC chips that package everything into one chip that you could single-handedly put on there? Do you buy a chip? Or how do you think about board construction? Like, there's a lot of micro decisions that have to be made on avionics side to make it work in space.
Yep.
The challenge here for us is that this will be one of the most power efficient spacecrafts ever built. And I think the only one that'll be better than us when we launch will be DART. DART was about 10.5 watts per kilogram. And we're going to be just over 10 watts per kilogram. So it's a very power efficient spacecraft compared to anything else that's ever flown, which means it's really difficult to get it right.
No pressure, right? Well, a lot of it, we're a little bit easier with which parts we're going to use, right? So we don't have the weight of the dinosaur space industry upon us.
What do you mean by that?
I mean, using a part that, using parts that are RLAT tested, radiation hard, they're going to work every time. You don't, that if they fly around the sun or they fly around the earth for 30 years, they're going to be okay. But they're also very expensive and they're very slow because, it takes when I was at Honeywell, we always joked that, we were 15 years behind the technology because that's where the radiation hardened parts were. It's like they were older parts. I mean, we were using a rad hard 603E like years after I worked there. I think they've finally gotten rid of it. They may still sell it. I don't know. But that's the thing is like you get something that works and it does what they need it to do. And that's what they're going to use forever. Right here, we're trying to do something different. We're trying to do it, more efficiently. So while we have to be careful about what parts we pick out, but we don't have I don't have 100 kilorads radiation requirement. It's much less, lower radiation requirements, trying to make sure that we're going to be safe if we get, single events and such. But, we have a different risk posture. And that's, that's kind of like what New Space is all about is a different risk posture.
Yeah, but we don't get it for free. What it does mean is that the burden is on us to now go test this stuff when it's assembled. And so what we actually do and what we did on Odin is what we'll also do on Vestry. And this is like, we go build it, we go put in proton beams and we test it and we see what we get. And we may get answers we don't like and have to fix them. But the piece parts program selection here is not based on space rated parts. SpaceX in the early 2000s actually did a massive study on this, and it's really interesting to go read it. I don't know if it's public or not. If it's not, email me and I'll send you the PDF. But what they did is they looked at space rated parts versus automotive grade parts. And the big difference there is that space rated parts can be manually fixed. And over time, what they actually showed is you get less reliability out of a space rated part than you do out of an automotive part because automotive parts aren't fixed, they're thrown away. And this helped a lot with building. And it obviously has created things like the Falcon rocket. It's created things like Starlink and Dragon. And everybody's kind of adopted this for low Earth orbit. Low Earth orbit is about a third of the radiation that we get in deep space. It's not an order of magnitude less, right? It's actually pretty close in some essences to what we get. And we want to see if that same avionics strategy can work when we go beyond the Van Allen belts and beyond the protection of Earth. That's kind of how we're thinking about it a little differently. And so time will tell if we're right? I don't think we're going to know if we're right until we do it.
Yeah.
What are the other challenges for deep space? Like, your job is very different than if we were just building satellite comms.
Well, the difference between deep space and the satellite comms. I think you probably talked about this before, but thermally, we're in the sun all the time, right? Yep. So that's different. It's different than I've had to deal with because we get, and I'm not sure if it's better or worse, frankly. I mean, if we don't get too hot, it's probably better.
Yep.
Because then we don't go through all the cycling, and the cycling is one of the things that really kills the electronics. Going around the Earth.
Well, I'll tell you this: it's worse.
It's worse.
It's worse
because it's hot.
Because it's hot.
That's
Think about it this way. If you're sitting in your Mojave Desert trip, right, your car broke down with no air conditioning in the Mojave Desert, like night comes and it cools down to 90 degrees and you can live, right? It goes from 130 to 90. That's all great. Same thing happens on a spacecraft, right? When you go around Earth, like you're going to cool down and then heat up and cool down, and it will help stabilize temperature.
Right.
The problem we have is that we're so thermally small, right? This is an extremely small 200 kilogram spacecraft. It has a dry mass of about 140 kg. That's not a lot of actual material to put heat into, and convection doesn't work in space, so it's all radiative, right? Most deep spacecraft are an order of magnitude bigger. I mean, Psyche's what, 3 tons, 4 tons? DART,
2,700 kilograms.
yes, 3 tons. DART was 600 kilograms. It was 3 times the size, and that means there's a lot more thermal mass to dump it into. We don't have that from a structural standpoint. So all that waste in your avionics, we have to do something.
I don't
with
waste anything. It's all great. It just warms it up too much, right? But honestly, if the temperature can stay hot and doesn't get too hot, then that'll be fine.
Yeah.
It doesn't play into your reliability, because the hotter you are, there's sometimes called erroneous equations or Arrhenius equations, but we like to call them erroneous equations because they're just making stuff up. But they, as you get your parts get hotter, they don't last as long. In fact, they do like accelerated life testing by making them hot and running them for a long time, so they don't have to run them for really long. But like I said, if we're not cycling, we're not going to crack stuff, and that's where the cycling comes in. Is that your solder joints, and it's not so much the parts themselves that are going bad. It's the connections, the interconnects, and all that, and you get a lot of expansion and contraction and. I don't know. The thermal guys would tell you that you got some coefficient of thermal expansion, CTE mismatches, where one thing expands different than another, and that puts a lot of stress on stuff. And they put a lot of effort into making those and matching those and doing this and that, but you're using such vastly different materials that it's impossible to match everything up, and you're going to get stresses. So without that, that's great. But like you said, it's hot. And so we have to deal with the heat.
Or cold.
Or cold.
Right. On the other side, it's really cold. So
yeah. Could be.
Yeah.
Right. On both sides, we have problems, right? So
by the way, we also can't just rotate the spacecraft. We're going to get this question, right? Like, well, why don't you barbecue roll?
Yeah.
Pretty common tactic to help spread heat around it. And the reason is because of radiation protection, right? We build one side of the spacecraft to be very susceptible to radiation and block it with shielding, and the other side is not. So we don't want to roll into the non-shielded side.
Yeah.
Why do you only shield one side?
Because of mass. We just don't have the mass to shield everything. I mean, you need 3.5 millimeters of aluminum to shield one side. You can use some other materials there as well. There's a whole bunch of different ways to look at this, but there's one simple equation here. Shielding equals mass. Yep. And if we do it on one side, or really 2 sides because it's a cube, it's a lot less than if we do it on every side, all 6 sides of the cube, right? So it's a way to save a lot of mass on the boxes. And the avionics boxes are fairly large. They're not insignificant weight. They're about 10 kilograms a piece, and we use 2 of them.
You mentioned earlier that this is one of the most power efficient on a watt per kilogram, I think you said. Why is that important, actually?
It's not that it's important because it makes it really hard to build. If we take in less power, if we take in 100 watts of power, like all this thermal problem, it's really easy to put. Yep. You could dump 100 watts of power into just our aluminum structure of the spacecraft, and it'll radiate out fine. Right, we actually might get too cold. It's a different conversation, right? But from a heat perspective, we won't get too hot. When you're all of a sudden generating with solar panel 2,100 watts, that 2,100 watts is going somewhere. And it's either going to be used and thermally put into an avionics box used by our thruster, which is the real hope so that it's outside the spacecraft, right? Or we have to radiate it. And so what that means is we actually need massive radiators to disperse that much energy out of the spacecraft. There's no other way to get rid of it. So the spacecraft will heat up to an ambient temperature that's fairly high in this case, and that's the only way we can keep it small.
Do you have to plan for a scenario in which you're dumping all of that power out through a radiator, or is there a percentage that you plan for? Yeah,
no, it's actually more than that, because
okay.
the solar panels that are making that are only about 30% efficient, maybe a little more, and those are really efficient solar panels, and the rest of the energy that's coming in, the other 70%, is just coming in as heat from the sun. Right. So we're always radiating away 70% of the power that the sunlight that comes at us, and it's got to go out the back of the panel. But in addition to that, if I'm not firing the thruster at the moment, and I'm only using 200 of my, 2000 watts or whatever, the rest of that power also is just sitting on the solar panels, and has to be radiated away. we're building a system that doesn't shunt the power to the, but it ends up being the same. So normally they take they have the power come in and they shunt it basically short some of the solar cells out, and that basically dumps the heat onto the solar panels still. And we're just not turning them on, which ends up being the same thing as they don't conduct any power away. So all of that heat stays on the solar panel. So at all times, you can look at it this way: at all times, we are radiating away all the power that comes from the sun in one way or another. And it may be coming from we may be lucky in going out the thruster and actually doing us some good. But other than the thruster power that's going out the thruster, which is, again, you get into efficiencies and whatnot. It's our PPU is, I think, 80% efficient or something like that. We take in 1.2 kilowatts to give the thruster a kilowatt, but the kilowatt isn't all going out of the thruster either. There's only a set percentage, and I'm not sure how efficient that is off the top of my head, but the thruster gets really hot too, and that has to radiate.
The thruster gets really hot. The thruster is really isolated from the main avionics of the spacecraft, so we don't have to really worry about the heat that's built for it. But it's always interesting to think about thermal in space. For instance, when the thruster is firing, the solar panels actually get colder. Because we're taking power out of the panels. So it's just this very different equation and way you have to think about it. And it's all based off one equation that you can go look up. And that's how we get the steady states and figure it out. Yeah,
that's the thing. It took me a couple of weeks to wrap my head around that. And to be truthful, is after I got here, because I'm looking at the whole power system, I'm like, where's this power going? And it's all coming in. And it's like, well, it's going exactly where you think it would go. It's either coming from the solar panels or it's sitting on the solar panels and radiating away. There's really nothing else for it to do. And once you get, once it got past the obvious, it was, it becomes a little weird, but it's a very strange way to think about power and heat and stuff.
And it's just because we don't have an atmosphere, right? On Earth, this actually happens the same way on Earth. You just have an atmosphere, which is actually much better, maybe not a better, but it's a different conductor of heat.
It's better.
It's better.
Yeah.
So like your solar panels on the roof do the same thing. They just take it away with convection instead of radiation.
Right. So when you're on Earth, you radiate your power too. It's just it's mostly being conducted away by the air, right? So you get much better cooling because there's something there to just blow by and take it away. And you instead of heating up the metal and then having to radiate it away, which is, not nearly as easy. You imagine if you just leave something sitting on, you leave a hot pan or something sitting on a table to cool off, it's still getting affected. But if you put a fan on it, it's going to cool faster, right? And that's kind of like, that's where you get your conductive heating or convective heating out of the way. And it's much more efficient, and it makes the whole designing electronics much easier, which is something I've never been able to do really. Hardly.
There's no fans in space.
There are
none that work at least.
Right. You can put them there, but you're just wasting. Wasting more heat. They're actually generating heat because you'd be powering them.
And just moving nothing.
And moving nothing. Yeah.
You're building out your team right now. What are you looking for, and what makes someone successful here?
Gosh, you have to be able to adapt really fast, right? We're moving very fast. First off, it's the speed, with which we're trying to do this is
it's easy to say that. Help ground that for someone. Like, what does that actually mean?
Well, let's see. So a lot of the times in a job that moves a little bit slower, you figure out everything that you're going to do in a system, and then you decide how to do it. And you've got time to do all these different trade studies to figure out how the whole thing goes together. And then you can pick out, parts, and you can do studies to see that they're going to fit and everything like that. Here, it's more like, all right, I've got to figure out what I'm going to do, and I have to do it. And I can't figure it all out at once. I have to figure it out a little. You have to take it off in chunks and do your system design and your architecting and your implementation in a very close time frame, right? And sometimes you get down a little path, and you have to be able to adapt too, because you can go down a path and it can be wrong. And the difference here than, say, traditional aerospace or dinosaur aerospace companies is that we try to iterate. That's the new space thing, is to iterate. They say move fast and break things. I don't like that saying very much, but it kind of applies, because you move fast and you find out where it doesn't work very quickly. It's easier to get it's frankly, it's easier to get a board built in 2 weeks and test and find what's wrong with it than it is to spend 4 months simulating and, every little dotting all the I's and crossing all the T's. It's like, oh, well, that part's too hot. I've got to do something about that. Or, it's very much easier to see when you get it and it's faster. But that means that you have to be very adaptive. You have to, I've got this, I had 3 strings on each wing of my solar things or my 4 strings. And now I have 3 or 6, one of the two. I've got to change the number. But you got to kind of be able to roll with changes like that and be able to find out be able to do things that you don't necessarily know everything about, right away, and just get as far as you can in a design to find out where it breaks.
Okay.
But it also comes to the selections we've made at the high level. The reason that you can't apply this direct thesis to like JPL is because they don't build everything themselves, right? So we apply this everywhere, and it only works if you apply it everywhere. We're talking about with the solar panels is because we can literally walk over to the people building the solar panels and say, why are they different? Why are the 3 different? We want them to be the same. And if they're the same, that means we either have 3 strings or we have 6 strings. That's the dividing line. We can't have 4.
Yeah, and that was that discussion we had this morning was actually really kind of shines a light on how we operate here, right? Because and what Matt does is walk around and ask questions, right? Poke at us, and it's like his thing. And he found that we were in a loop, a logical loop. He's like, why are there 4 strings on the solar panels? It's like, well, because Chris said he needed 4 strings to match his electronics. And then it's like, well, why was that? It's like, well, because when I started, there were 4 strings on each panel. So then we get into this loop where I have 4 strings on a panel because there are 4 strings in my electronics. And I had 4 strings in my electronics because there were 4 strings on the panel.
Yeah.
And then we didn't go back and look at, all right, well, we're changing some stuff.
Yep.
Does it make sense to change the number of strings or not? And Matt,
Well, the cost of that meant that we could not have 1 backup panel per wing to do a replacement. We would now have to have 2,
right?
Because the wings are not all built the same. It also goes into the whole approach of like, we have to be able to iterate or build at volume. And so now instead of building 8 panels, we're building 4 of one type and 2 of another type, or 6 of one type and 2 of another type, whatever. I did that math wrong. You get my point. We're not able to build the number of panels that we need to kind of assembly style. We'd have to build different panels, and we don't want to do that everywhere. And again, it wasn't because there was some overlying engineering decision that drove that. It was just bad communication. And the luxury of having a 50-person company is we can all go meet in 2 seconds and make a decision and change it.
Yeah.
If this was at JPL, we would have had a design review board, then a requirements review board, then 40 levels of approval. And that all actually really needs to be there in place when you are buying a $50 million flight computer from Honeywell and a $10 million this from that vendor and this. Like, you can't do that because it's a contract change, it's a cost change, it's very different. We have the luxury of being able to do that because we're vertically integrated and building it all here.
Yeah, that was actually when I was in Honeywell first. This is how I got into systems engineering. Is they pulled me into a proposal to go and design something, and we'd lay it out and figure out, all right, this is the way we do it. These boards are going to do these functions and whatnot. And then as we were going through this very quick process to go and make a proposal, I respun how we were doing it like 3 or 4 different times, right? And ended up with like a pretty efficient packaging and design thing. We lost the bid anyway, but doesn't matter. What mattered is that it was like, oh, well, you're doing system design work. You should go comes into the systems group. And I did that. But the difference here is that I can still change it. If we'd gotten to the point where we won that bid, that was done. It was locked in. That was how the system was going to be. And for the next 3 or 4 years, everybody was going to be working on the decisions that I made that were then set in stone, right? And here, Matt can come, what are you guys doing? And we can go, I don't know, man. What are we doing? And so, we talked about what it was we were doing and figured out we were doing stuff that we didn't have to. So now we're going to see if we can do it in a little bit different way, but that's something that can change. Whereas if we were in, Dino space, we'd already be down, the subcontractors would be halfway through building our solar panels already. Right. And we wouldn't be able to change it. But like Matt said, because we're all here and building our stuff, we got that flexibility.
Nice. I think that wraps up. Anything else on avionics we want to touch on?
Do we got questions?
We have questions.
All right.
All right, cool. We're going to roll this into mailbag questions. So
can I just say really quick, though, before we do that, how much nicer was this to talk without Robin?
I mean,
It was nice, smooth.
Robin's good for some things.
Just don't be
I
on
think
Team Robin.
Robin's great.
Robin, if
Go
you're
to the
listening,
questions.
We love you. All right, this is from Levi. I think, Matt, this is generally to you, but I'm going to abstract this out and let both of you answer. We recently made some buzz around Cascade Space that just came out of Y Combinator. They are solving a deep space comms issue that we've talked about before. The question is, what are the problems do you wish someone else would go solve for us? So I'm going to let each of you put an answer out there.
What do I wish that somebody else would solve?
Yep.
Well, that's a little boring, right? I like solving the problems that we have, but
Well,
I guess
you're gonna
honestly,
yeah.
I guess I would like to make sure if somebody could guarantee that our radios would work and we would talk when we launch, that would be great. That
Okay.
would be.
So you want a new
favorite.
radio,
I just have a new
radio company.
Well, I have a new, my new RF guy started last week when I wasn't here, and so I hope he's going to do that for us and make sure it all works. So,
Okay.
yeah,
All right.
everything else I can handle.
So Chris is putting out feelers for radios. Matt, what are you asking for?
I think that it would be really cool to have a high volume chip company go into production on a chip that was much more stable for radiation. We have to buy very specific shielded microprocessors right now. And what you can't go do is get an Apple M4 chip and put it on this thing. I wish you could, and there's some technologies out there like these what are they called? The FinFET transistors that have some promise. There's obviously the silicon on insulator technologies that have some promise, but nobody's gone into scale with them at a level where we can go do this. The problem with these little microprocessors we get or microcontrollers we get that are space rated is they don't make a lot of them. And so there's not a community there. It's not like I can just, apt get install Linux on it, which I know all software guys are not a real command, but I like it. There's not things that you can go do on there at a high level. A lot of this is us actually going back down to writing machine code, figuring out registers. It's a really big problem, and it really takes a lot of time, and that just comes from scale. So I wish there was higher volume ASICs available that we could fly.
I've internalized that wish so much that I don't even say it anymore. That's been for 20 plus years I've been doing this. That's been wouldn't it be great
to bring that down?
Wouldn't it be great if we could have better chips
Yeah.
for space? Yeah.
Okay. Keeping on the comms thread, this is from Abraham. So his observation is the deep space network is increasingly strained and reliant on aging RF infrastructure. Are we considering integrating or testing optical comms on future spacecraft?
So I will say this first off, DSN is not relying on ancient radio technology or anything like this. DSN is exceptional. The problem is it's a premium product that I cannot afford. Like, it's really that simple, right? It is the Gucci of spacecraft communication, and like we're at Walmart right now, right? And that's how we have to think about it. I cannot go spend. This is why some of these missions, and if you look at the recent NASA budget, you're going to see actually really, really big line items to continue these missions. All that is paying for DSN time. It's extremely expensive. I mean, you have 70-meter dishes out of Goldstone. You have cryogenically cooled receivers, top-notch RF equipment. And the modulation they use is BPSK. It's really, really old school form. It's one of the first forms of modulation, right? That's what works in space. You can't do 5G, right? It just doesn't work at the signal noise ratios we have, not in deep space. So I want to be careful with what we say about DSN or how we think about radio. It is the cream of the crop of what we'd want to use.
Anything from you?
I don't have a lot to add to that.
Okay.
I would think that pointing would be very hard with an optical from way far off. And we have enough. It's hard enough as it is.
Optical comms are great. The challenge with optical comms is that atmospheric attenuation is a big problem. And so if there's clouds, if there's different temperature, it's really hard to get to the ground. It actually doesn't fix the problem of RF. You still need a gigantic light collector to collect the laser coming back. And it's being tried on Psyche right now. There is a laser comm system on there that they have worked. It works very well. The dishes to get that are more expensive than DSN time. So that's the problem right now. Now, hopefully in the future, all these companies will come up and please, maybe this goes back to the first question. If anybody wants to go build giant ass light collecting dishes for my laser comm system, I'm happy to go buy them from you for Walmart prices. But they got to exist. And right now, that is a government owned asset that it's just not worth us trying to get access to put a comm system on our spacecraft. That's not free mass on the spacecraft, right? That's actually a pretty massive unit to put on there.
Yep.
I just point out that Matt insulted my hometown, and then he keeps bringing up Walmart over and over again.
Oh, yeah. Yep.
As the cheap solution.
Cheap solutions work, man.
They do sometimes.
Hopefully.
Kmart.
Two more. This one's from Jordy. Hello, miners. What happens if there's a layer of dust or gravel on the asteroid? Does it affect how our mission architecture or our mission architecture or mining architecture works?
Well, the hope is that there is no layer of gravel or dust, and this is why we look at the spin rate of the asteroids along the equatorial regions, so we know if centrifugal force will have thrown it off or not. Now, it's really hard to account for other forces that are going to bond to the surface. There's quite a few scientific papers about whether or not this is a good idea or a bad idea that we'll say, but it also matters the level of dust. The honest truth is if we have a little tiny layer of dust that's, like 3 micrometers thick, who cares?
Yep.
Our ability to land on it is not really hinged by anything. Our ability to mine it is not really affected by anything. But let's look at the other way, that it's a Bennu. Like the honest truth is, then we're just going to hit it and sink to the bottom, and that's not a viable target. So it's really hard to answer this question. I think what's really cool about what we're doing is we have some theses that we want to go after, these spin rates, how they spin, how we monitor them, all these kind of things. And we work with a lot of scientific advisors to help us better understand this. We're going to find out a lot when we get there. And that's why it's so important on the next one to show up, right? We got to show up to the party and see how cool of a party it is. It might be a pretty shitty party.
But I think the other thing that's important to pull out of that is we think about it less from are we able to mine it, and more are we able to maintain contact with it?
Yeah, are we able to land on it? We do not have a viable solution. By the way, we don't have a viable solution really to land on a carbonaceous asteroid, a stony type asteroid. Like NASA has, and JAXA and some other have done this before. It's really difficult at the sizes we're going after. We don't have any complicated ways to land, right?
Yep.
If it's not ferromagnetic and we cannot stick to it, we're not landing on it with the next vehicle.
Yep. Well, that's a great layup for the next section, which I call the call is coming from inside the house. Someone who will be unnamed.
Put the name out there. Blast them. Who is it? Who is it?
I'm gonna give this to our avionics guy.
Uh-oh.
How can we land without legs?
Gently.
Okay.
We're putting fucking legs on a spacecraft. Who is this? Who is it? I'm going to go fire him. I'll see you guys later.
I think they have 0 in the mass budget right now. So
yeah, there's not a whole lot in the mass budget.
Not a whole lot in the mass budget yet. I think, if we can crash land without legs, but we need legs.
No, we can't. We just bounce off it. That's not a landing. You don't crash land and bounce off it.
I think Matt might be right on this one, though.
Nathan would like you to think a little bit harder on this.
Fucking Nathan.
All right, that's all we have for today. Chris, thank you very much for talking avionics with us. That's a wrap. Tune in to next week's episode, which is undetermined yet. So we'll figure that out next week. All right, thanks, y'all.
Great primer.